Alright, welcome back to this our channel, and today we're covering three topics: momentum, energy, and then we're gonna do a final example combining momentum and energy in collisions. So let's start out with momentum. So our definition of momentum is mass times velocity, and it's represented by a lowercase p. Don't get it confused with power, which is an uppercase P, and we covered that in the last video. So the units of momentum are going to be a kilogram times a meter over seconds. So momentum is basically like inertia in motion. It's really like a measure of like how hard would it be to stop the object that's moving. So in this example, we have a skinny little guy running at speed v, and then we have a big fat guy running at speed v. And in this case, the big fat guy would have a greater momentum since he carries the bigger mass and is more massive. And that's basically what we mean in our definition of momentum. Now we're moving on to energy, and you might recognize these two equations. I brought them up in the Robin Hood swing problem video that we did, and they're both measured in joules. And we see that kinetic energy is 1/2 mass times the velocity squared, while potential energy is mass times acceleration due to gravity and times a change in height. Now, we talked about work in the video a couple videos ago, and there's a cool relationship between energy and work that is useful in some problems, and I'm just going to briefly write down the equations because you might need to know them. So we have that for kinetic energy, it's still called the work kinetic energy theorem, and basically says that work is equal to the change in kinetic energy. So work is basically equal to KE final minus the initial kinetic energy. And these are useful in problems where you're given energy and some forces, and you need to determine maybe like the work done or velocity or something, because you have velocity and forces and work and kinetic energy. And now another distinction to make, it's pretty important, is change in potential energy is equal to the negative work. And so essentially when you it's equal to the negative work because what's going on is force of gravity is opposing the motion. So if you're pushing something upward, force of gravity is opposing the direction of motion, and that's going to give you a negative value for work. So when you have a negative of a negative value, you're going to get a positive value. So that's why when you lift an object, you're going to have, and you're doing work on that object, you're going to have the force of gravity is doing negative work, and you're going to have an increase in potential energy. So that's basically, those are some relations relating energy to work, and they're kind of important to know. So I'll leave those up there. All right, now we're going to move on to momentum and energy in terms of collisions. So now there's two extremes of the collision spectrum. It's kind of a spectrum. On one end, you have inelastic or non-elastic collisions, and this is where kinetic energy is not conserved, but momentum is conserved. And then at the very far end of the spectrum, in an ideal world, we have perfectly elastic collisions. And when it's a perfectly elastic collision, the kinetic energy is totally conserved, and the momentum is also conserved. And as you notice, in all collisions, just remember this, all collisions, momentum is conserved. And what defines a collision is whether or not kinetic energy is conserved. And so in perfectly elastic collisions, kinetic energy is conserved. And remember, in the real world, most collisions fall in between perfectly inelastic, which is when two objects stick together, and the spectrum all the way to perfectly elastic. So on one end, we have perfectly inelastic, and then we have like the spectrum of collisions, and then we have perfectly elastic on the other end. And this is the real world collisions. They fall in between these two these two spectrum on that spectrum. All right, so now we're gonna do a simple problem just to incorporate these two topics and collisions. Pretty simple. It says two balls collide and stick together. So if they stick together, we know that's gonna be a perfectly non-elastic collision. So if they ask you about that, just remember that when it's stick together, it's perfectly non-elastic. And they're asking, what is their final velocity? So when you're approaching this problem, whenever it's a collision, just we know that momentum is going to be conserved whenever. So what we want to do is write our conservation of momentum statement. So we're going to say that initial momentum is equal to final momentum. And so we're going to use our equation from over here. So the initial momentum, we have one block, we have two blocks and they're separate. So it's going to be M1 V1 plus M2 V2. And then in the end, they stick together. So they're going to have a single velocity and their two masses are going to be combined. So we're going to represent this by M1 plus M2 times, let's just call it velocity final. So now we're going to rearrange for the final velocity and then we'll plug in the numbers. So velocity final is going to be equal to M1 V1 plus M2 V2 over M1 plus M2. We plug in, let's see, so it's going to be 10 by 5 plus 2 times 10 over 5 plus 10, and that's going to give you, let's see, we have 70 on the top over 15, so it's about 4.66 meters per second. So there you have a basic example problem of momentum. Just remember, momentum is always conserved in collisions. Remember these definitions of momentum, the definitions of kinetic and potential energy. And if you asked for problems with like relating work and energy, these two relations can come in handy. All right, that's it, and see you next video.